Hello, my name is Joe Raphael, and I'm doing an overview of the current usages of AI in radar applications. So, my reason for exploring AI in radar applications is that with the rapid development of AI and machine learning related technologies, it's obvious that such a robust and powerful technology be utilized in radar applications. So, I'm interested in exploring this topic because I'm curious to know how AI can be used to further radar research or application. And by researching this topic, I hope I can gauge what aspects of radar development can be handed over to AI and what aspects must be handled with a careful and discerning human mind. So, glimpsing over the various research, it appears that AI has had use in signal processing, filters, target detection, estimation, and radar imagery, and furthermore, I want to understand how flexible using AI is for using these in various applications. So, this paper examines how the use of AI can be validated enough to be used for military use, and then applies the AI validation technique onto a radar application. So, starting off, one might ask how engineers validate and test products or their designs. And one way to do it is called the digital engineering approach, in which engineers create a digital or simulated environment referred to as the digital twin, and then test their product within this digital environment. And so, one might ask, uh, how can we validate AI using this process? And this paper suggests a framework for validating this AI, which consists of three phases. The first phase is the baseline phase, in which we create a base environment and assume there are no modeling errors. We then apply extensive Monte Carlo simulations until we reach statistical convergence, and then supplement this analysis with real data, as in data obtained by performing actual physical tests of this spoken system. And then this defines the base performance of the system. The second phase is excursion, in which the system is subjected to low probability events and the performance of the system is then measured again. And then we apply more Monte Carlo analysis to make sure that we reach statistical convergence. And then the final phase is called the black swan phase, in which and black swan phases are highly unpredictable, highly unlikely events that could very well happen regardless and are extremely disruptive. So systems should be tested against these events to more accurately measure their robustness. Which leads to the next question. How can we think of these statistically impossible events? Fortunately, researchers have used AI to generate what these events could be like, since AI has this unpredictable element that is still constrained by realism. So this paper applies this approach to radar application by having multiple convolutional neural networks and that were fed an input of range Doppler data from a ground moving target indicator radar, and then trained to output an estimate range and Doppler of this target. And after applying these three phases to validate the AI, it's concluded that the AI is reliable enough, and that the figure on the slide shows that the respective performance of the AI. The next paper uses a neural network in order to increase the efficiency of the target detection algorithm. More specifically, the general idea is that researchers intentionally lower the thresholds for detection and binary integration so that more targets are allowed to pass through. However, doing so will increase the amount of potential ghost targets or false alarms, so researchers compensate for this potential increase of false alarms by employing the use of a convolutional neural network to determine if these resolved detections are just noise or an actual target. And the signal processing used in this paper is outlined as follows. First is the coherent processing interval, in which a set amount of CPIs are transmitted and collected. The collected quadrate data for each CPI is then processed with pulse compression and Doppler processing in order to output the range Doppler maps. The maps are then inputted into the cell averaging constant false alarm rate detector, which outputs a list of possible detections organized by CPI and the SNR of the detection. Finally, the detections are organized into centroids and processed for the averages of each cluster. Next is a disambiguation processing, which starts off by taking the input list of the centroided detections of each CPI and then extracting the range and Doppler data from these detections. The extracted data is then processed by converting the range bin to meters determined by the range resolution of the radar. We then map back the unfolded range and velocities to the range and Doppler bin for each CPI. Solving the bins with the 2x2 matrix of ones, we finally sum all the detections for each CPI and then use the M of n criteria to determine which targets are real. With the signal processing architecture outlined, we can now examine the results. And based on the table, it can be seen that for some configurations, neural network assisted signal processing architectures can outperform the baseline architecture by having higher probabilities of detection, which is PD on the table, and having lower probabilities of false alarms, which is PFA on the table. Conclusion. AI has been shown to be capable and effective when integrated with radar applications. However, it's important to note that it's not used to completely replace entire architectures. Instead, it is used to augment or supplement existing processes and constrain and validate it to a great extent in order to ensure reliability and accuracy of the AI output. As research into this area further develops, the questions one might ask are, which AI architectures are the best and for what aspects of radar, and what are the trade-offs?